Okay, good morning, everyone. So our speaker today is Zhanar and Berikkyzy, and Zhanar will be speaking on long cycles in balanced tripartite graphs. Thank you, Zhanar. The floor is yours.
Thank you for the organizers for this opportunity. Today we'll talk about long cycles and balanced tripartite graphs. This work started at IMA in 2019. There was a workshop for women in graph theory and applications, and our group, here's a picture of our group. So we have from left to right, Linda Lesniak, myself, Jill Faudree, Jessica McDonald, Gabriela Araujo-Pardo, Rachel Kirsch, and Kirsten Hogenson. So the outline of the talk is we'll consider some degree conditions for Hamiltonicity and long cycles, and then that will be the first half of the talk, and then the second half will focus on edge conditions that guarantee Hamiltonicity and long cycles. The first half will sound a lot like a survey, but if you do have any questions or if you notice any mistakes or you want to add anything, please feel free to interrupt me at any point. Okay, so degree conditions for Hamiltonicity. So, and I'll be writing, I hope that's okay with everyone. Just a couple things. The graphs will just denote them by G, the set of vertices V and set of edges E. I'll often denote E of G to be just the cardinality of the edge set. We'll have okay, so if I'm using some notation and you're not sure, please let me know. But there's all the standard notations like the minimum degrees and degree of a vertex and things like that. Graph is Hamiltonian if it contains a cycle that, or if it has a cycle that contains all the vertices. Right? Okay, so let's start with the degree conditions for Hamiltonicity. Now, there are many results. Again, this is a big problem in structural graph theory, one of the classical problems. There are lots and lots of results. So I'll just mention the ones that are most relevant for the talk. So of course, I'll start with Dirac's famous theorem or Dirac's condition 1952, given a graph on n vertices. And I'll just write down the condition. If the minimum degree is at least n/2, then the graph is Hamiltonian. Right, so that's Dirac's condition. And Ora in 1960 showed that if G is on, again, graph on n vertices, and degree of U plus degree of V is at least n for any two vertices that are non-adjacent, then the graph is Hamiltonian. Again, I'm just writing the conditions, so this looks, it might not look, it doesn't look like complete sentence, but we're just saying graph on n vertices at least n/2, then the graph is Hamiltonian. So these are the results for general. Then the patterns today will follow would be general results, bipartite results, tripartite, and k-partite. So for bipartite case, so this was considered in bipartite setting by Moon and Mosher in 1963. So given a graph that's balanced bipartite, so G is balanced bipartite on two n vertices. On two n vertices, and so if the minimum degree of G is at least strictly greater than n/2, and then the second condition is if du plus degree of U plus degree of V is strictly bigger than n for any UV. Actually, here U and V must be non-adjacent. Let me write this way. The vertices, UV non-adjacent, and actually, let's say U from V1 and U2 from V2, and they're non-adjacent. where the vertex set is v1 plus v2. So essentially what I'm trying to say is you want to make sure that these non-adjacent vertices come from two different partite sets. Then the graph is Hamiltonian. So you can see that the Moon and Moser reduced Dirac and Orra's conditions by a factor of 2, even though they look the same. We have 2 n vertices here. So next, people consider tripartite graphs. Or actually general case. So Chen, Faudree, Gould, Jacobson, and Lesniak. So this is 1995. So they came up with a minimum degree condition for balanced k-partite graphs. So G is balanced k-partite on kn vertices. And I didn't mention before, balance just means the cardinality of each partite set is the same for all partite sets. So given a graph that's k-partite balanced on kn vertices, if the minimum degree is strictly bigger than k over 2 minus 1 over k plus 1 times n when k is odd, and k over 2 minus 2 over k plus 2 times n when k is even. Again, I'm just writing the condition. If the minimum degree is strictly bigger than this, looks like my iPad is a bit lagging. But if the minimum degree is strictly bigger than this, then graph is Hamiltonian. So Chen and Jacobson, and we will use this theorem at some point later in the talk, in 1997 showed that, again, same balanced by k-partite on kn vertices, if the degree of 2 non-adjacent vertices is strictly greater than 2 times this number that we have above, for any UV non-adjacent, and again, we just want them from different partite sets. Okay, so so that's the condition for k-partite balanced graph on kn vertices for it to be Hamiltonian. Okay, 2 more conditions that I'll mention, 2 more degree conditions that I'll mention. They will be relevant at some point. Any questions so far? No. Okay, 2 more conditions. They look a little different from these, but they will be important later. So Poja's condition, 1962, if for any r between 1 and n over 2, and graph is on n vertices in this case, if the number of vertices of degree at most r is strictly less than r, then the graph is Hamiltonian. And I don't know if I have enough room for Moon and Moser. I think I can squeeze this here. So it's in bipartite setting, 1963. So again, for any r where r is between this, again, the condition looks similar. We just want to make sure that each vertex from each partite set, well, the number of vertices is this, and now I'm missing, I can't fit 1 and 2, so the partite sets v1 and v2, and the graph is on 2n vertices in balanced bipartite. Again, kind of squeezed in there, but Poja's result on in a bipartite setting. Any questions? Okay, so now the next natural question would be, or next natural step was, what about Hamiltonian -1 cycle or some long cycles, right? What are the degree conditions for those cycles? So if we want a long cycle instead, so again, we'll consider the general settings and the bipartite and tripartite and see where we have gaps and what's known and or unknown. Okay, so oh, I guess before I mention this, I think I forgot to say that DiBiase very recently, was it in 2019, right? He considered this because these are always for balanced, both of these results. So DiBiase et al., they considered unbalanced in an unbalanced setting. Maybe I'll just quickly write it here. Different colors so you can see. This is 2019, so unbalanced version for k-partite. It looks a lot complicated. They've tightened the results asymptotically. So, but it's really nice result available out there. Okay, so for degree conditions for long cycles, I'll start with Dirac again, 1952. So given the graph that is, so it let G be two connected and C be a constant between 3 and n. If the minimum degree of a graph is at least C/2, then there exists a, I'm just going to write C plus cycle, which is saying that graph contains a cycle of length at least C, right? And so if we replace C by n, this is exactly his result for Hamiltonicity, right? Ory's condition was generalized by Bermond in 1975. So G is two connected. C is between 3 and n. If the degree of any two non-adjacent vertices, degree sum of non-adjacent vertices is at least C, then the graph contains a cycle of length at least C. Again, here we want U and V to be non-adjacent. Okay. So again, those are the general results. Then the next step is, okay, what are the conditions for bipartite graphs? So Adamus and Adamus recently showed that if G is two connected, balanced bipartite, on 2n vertices, if a degree sum of two non-adjacent vertices from two different partite sets is at least n, then there exists a 2n minus 2 plus cycle. So this is essentially the next step towards the bipartite case. And again, I'm not writing what are the conditions in U and V. It's always the same. We just want them to be non-adjacent and from two different partite sets. And they conjectured, so this is where the gap is. So they've conjectured that, again, if the graph is balanced bipartite on 2n vertices, and the degree sum is at least there it is, n minus k plus 1 for k between 0 and n over 2, then there exists a 2n minus 2k plus cycle. So there's a cycle of length at least 2n minus 2k. So essentially when k is 0, this is Moonen-Mosher, and k equal to 1 is Adamus and Adamus. Right. And I believe it's still open. Then I don't know of any degree conditions for long cycles. I'm sure there are, but I wasn't able to find any. I will quickly mention Poja's result. So he generalized.
Zhanar, can I ask
yes.
a quick question?
Yes.
So you don't need for the conjecture to the hypothesis of two connected anymore?
That's a great question. They did not state in the conjecture, but I'm guessing it is. I've noticed that every degree condition for long cycles requires two connectedness. So my guess is it's still needed. But that's a great question. Thank you. So Poja's result 1963. So he generalized his own previous result. So let me quickly state that G be two connected. We want G to be two connected. C be some constant between 3 and n. If for any r between 1 and c minus 1 over 2, if the number of vertices of degree at most r is strictly less than r, then there exists a cycle of length at least c. Right. So this is the last result I wanted to mention, and we recently proved. So you can see, I'm going to quickly scroll back. Sorry. So we have a Poja's result for Poja's condition for Hamiltonicity. We had Moonen-Mosher's condition for Hamiltonicity in a bipartite setting, and we do have Poja's result, Poja's condition for a long cycle. So there is no Moonen-Mosher type result for a long cycle, right? So that's what we proved very recently, just a couple of months ago. So let C be a constant, an integer. Again, we want G to be two connected, bipartite with partite sets be size at least C. So we not necessarily balanced. If for any for every partite set and every r between 1 and floor C plus 1 over 2, if the number of vertices of degree at most r, well, okay, I have to be careful here. This is for each partite set. So V from VI, the number of vertices of degree at most r is strictly less than r, then there exists a 2C plus cycle in the graph. Right, so this is a Poja's long cycle condition in a bipartite setting. Again, we don't require sets to be balanced. We just want them to have size at least C. there's this floor that we have. We believe it's tight. We do have two different pictures when C is even and C is odd that shows the tightness. But again, it's a new result that we're about to submit. I won't go over the proof, but I'll say that the proof does resemble very much Poja's original proof. Not this result. This is a corollary of his different result. So that original theorem that he has, it does resemble it a lot, and then kind of looks like we had to use a little bit of Moon and Moser's ideas and Poja's ideas and incorporate all of that. Any questions about this? No. Okay, so now I'll switch the gears and jump into the edge conditions. Okay. So again, there are lots of different conditions that guarantee Hamiltonicity and or long cycles. But we did focus on edge conditions a lot more. So let me start with a couple of things that we know, or some literature. So Ore 1961. And again, I'm going to skip a lot of details, but well, some of the things, but I'll mention. So this is a graph on n vertices if it has at least this many edges. So now we're talking about edges. Then the graph is Hamiltonian. Right, so this is one of the earliest edge conditions known. Later, Woodall generalized this from Hamiltonicity to long cycles. So this is 1972. If n is at least 2k plus 3 for some integer natural number k, and if the number of edges of the graph is at least n minus k minus 1 choose 2 plus k plus 2 choose 2 plus 1, then there exists a cycle in G for all L between 3 and n minus k. Right? So not just there exists a cycle, actually you have all these cycles from 3 up to n minus k. Okay, I have to think for a moment. Now this is best possible. You can see the tightness by, say you have two complete graphs, one on n minus k plus minus 1 and k plus 2, right? So you can see that it has this many edges, but has no n minus k cycle. So that's best possible. So again, these are the results for general case, and then the next step would be, okay, how do these conditions change when we introduce bipartite or tripartite conditions? So for bipartite graphs, Misham and Schmeichel is 1985. Given a graph that is balanced bipartite on 2n vertices, if the number of edges is at least n square minus n plus 2, then graph is bipencyclic. Right? So bipencyclic just means all possible cycle length, and because it's bipartite, you have only even cycle length. So this is for balanced bipartite graphs. Baga and Varma then extended it to unbalanced case. So let the vertex set be X and Y. We'll have partites as X and Y, where size, okay, so here's a condition. Well, okay, so where the size of X is M and size of Y is N, and the condition is if the number of edges is at least N times M minus 1 plus 2, then there exists a cycle for every L between 2 and M. And you'll notice that here, most of the edge conditions have not just this cycle, like a range of cycles, right? Either a lot of cycles, or this pancyclic or bipancyclic. Okay, so these are the bipartite cases. And so again, the next step would be tripartite. So Adamus in 2009 considered balanced tripartite case. So let G be balanced tripartite on 3 n vertices. And the condition is the number of edges is at least 3n squared minus 2n plus 2. Then the graph is Hamiltonian. So this is balanced tripartite case for Hamiltonicity, not necessarily not a long cycle. And later, Linda Lesniak and Daniela Ferreira have generalized this very recently to not necessarily Hamiltonian, but all, no, actually, Hamiltonicity, but not tripartite, general k-partite, and not necessarily balanced. So let G be a k-partite graph. Let's just call them V1 through Vk with size of Vi and I. And let's assume that the N1 is the biggest. And here is the edge condition. Okay, so this is the biggest, and say N is the sum of the Ni's. Now the condition is the number of edges is at least the number of edges of a complete graph, complete k-partite graph with these on these vertex sets minus n minus n1 minus 8 n2 when n1 is at most n over 2, then the graph is Hamiltonian. Okay. So essentially, if you have this complete k-partite graph with these vertex set, and you remove n minus at most n minus 1 minus 2 edges, graph is still Hamiltonian. Okay. Any questions? All right. So maybe I'll add add a page to just summarize what we know, because we'll talk about this for the rest of the talk. So we have Hamiltonicity results for edge conditions, and then long cycles, or I guess, yeah. So for general case, we had Orr, Woodall, then we talked about bipartite. And for bipartite, we had balanced and unbalanced, but they were both not necessarily Hamiltonian. It was Hamiltonian and long cycle, both, right? So Mitchum and Schmeichel and Bage and Varma. Right? So this was for balanced case and unbalanced case. Then tripartite. Right? So this is Adams' result for Hamiltonicity, and k-partite, Linda and Daniela, generalized, right? So Hamiltonian. So we don't these are the two gaps that we have for the long cycles, tripartite and k-partite in general. And that's what we have actually initially started the project with at the WEGA. We wanted to look at the next step, right? So the first thing that we proved is the following theorem. Given a graph that's, oh, I forgot to mention that this is balanced tripartite.
Let me just make a comment about your last summary.
Yes, please.
That there have been a bunch of results about what's called pancyclicity in graphs. In other words, you want to have cycles of all lengths from 3 up to a Hamilton cycle. And there is a literature about, somewhat in the spirit of what you're describing, about these so-called pancyclic graphs. And sometimes graphs are also what are called almost pancyclic. They'll lack a cycle of one length or a section of cycles of particular lengths, and people have looked at those problems also.
Thank you for that comment. Yes, that's really interesting. Linda and Daniela's also paper has some pancyclicity result in it as well. And you're right that there are a bunch of those, and somehow the edge conditions are different, I think. Well, it's my observation, and I haven't been in this area long enough, but somehow once you have Hamiltonicity, the edge condition allows you to go not just Hamiltonicity, go below all the way to the pancyclicity. But yeah, that's a good comment. Thank you. So going back to this theorem, and it was our first step in this direction. We thought, okay, we have a Hamiltonicity result. What if we go one less than Hamiltonian, so 3 n minus 1 plus cycle, right? And how large the edge set should be, and we want it to be a tight number as well. So this is a tight, and I can quickly, I guess, show the graph. Oops. Accident. N minus 1, n minus 1, and right. So that shows the tightness of the edge count, and it doesn't contain 3 n minus 1 cycle. So this, I guess I could quickly sketch this since we have time, but the proof was quite simple. For just going from Hamiltonian going down by 1 was quite simple, and then when we wanted to go down by 2, it got a lot more complicated. So first thing that we can observe is that if the minimum degree is small, there's really nothing to do, because you just remove the smallest degree vertex from the graph. The edge count is so big that we can just hit it with Daniela Linda's result, right? So you get a Hamiltonian cycle, and then you come back, because their result is for unbalanced case, doesn't have to be balanced, right? So this was quite simple. Just apply here, Lesniak. So we could assume that the minimum degree is at least 3. Then we wanted to use some of the degree conditions that for long cycles, but they all require 2 connectedness, which we almost got free as well. So if it's disconnected or has a cut vertex, the count just doesn't work. You have way too many edges here. It's almost complete tripartite, minus at most 4 n minus 5 edges. Okay. So again, we got the connectedness also from the count. So that was simple. So we have a huge minimum degree, well, big enough. We have two connected, so we can apply Poggia's. So Poggia's degree condition says if you have two connected, then for any R, if you have very few number of, okay, so you remember, I'll just say Poggia. So suppose we don't have 3n minus 1 plus cycle, right? So by Poggia, there exists an R between 3 and, remember the condition says C minus 1 over 2. So in our case, it's 3n minus 1 over 2. Such that the number of vertices of degree at most R is at least R. Right? So pick the smallest R that fails. And now we're just looking at some cases. It turns out that when R is, so we get a contradiction if R is small. Somehow, okay, so here's a key lemma. R is at least 3n minus 5 over 2, actually strictly like bigger than. So if Poggia fails, then R must be huge. Now, that's a problem because R is the number of vertices of small degree. Now you have too many vertices of small degree. The edge is, you just don't have enough edges, right? So why do we have a lot of small degree vertices? And this also falls out pretty quickly. Let's just count how many edges we're deleting. From the complete tripartite graph, right, to create G. Well, we have at least R vertices of degree at most R, right? Now, each one of them has to lose 2n minus R neighbors. They could potentially have, they could potentially all form a complete tripartite graph. So we have this, and all we do is just compare those two and get this. So that kind of comes almost free. So now you have too many vertices of small degree. You repeat the edge count, and you just don't have enough edges because it ends up being smaller than the 3n squared minus 4n plus 5. In fact, how many do we want, and where does this n at least 4 comes into play? Right here, right? We just needed n to be at least 14 so that we have at least 10 small degree vertices, and now we have 10 of them. And for the smallest, so we have 10 small degree vertices. For the smallest two, we just applied Chen and Jacobson. So we bounded their degree by 5n over 2. And then the rest are small enough that when you add them, you don't get enough. Now, the proof does look like a patchwork. You're just patching the things to get the result. And we're hoping to get a better proof. But it worked for this case. The next step was, okay, what if we want to go one below? We were able to prove that. So here's an edge condition for going, so this one below, in particular, 3n squared minus 6n plus 9, and again, it's tight bound. Except the proof difficulty jumped a lot higher because then we had to consider a lot of cases when minimum degree was equal to 3. So there was this minimum degree that we had to fight, and then number 2 is the two connectedness didn't come as free, so we had to fight for that, and it was really tedious. So then we said, okay, can we prove something that's general enough and we don't have to fight too much? Well, then we have to assume two connectedness, and we want the minimum degree to be big enough. Then we're able to get this general result. so that if the number of edges is at least 3n squared minus 2nl plus this number plus 1, then a graph will contain a cycle of length at least 3n minus l plus 1, right? So if we just plug in the numbers, say L equal to 1 case, that's Hamiltonicity, so that's Adamus, right? And we proved 2 and 3 above without two connectedness and without minimum degree condition, right? So they were more general. However, for L at least 4, we do have these two conditions in this theorem. So this is still work in progress, and large enough n in our calculations it shows something like 33. So we want n to be large enough. Otherwise, we're working on this. So the first thing we're trying to do is reducing the minimum degree. Somehow even reducing by 1 is causing us trouble, because the method that we use is the same. We want to apply POSIA, and we're saying, well, there is some R that fails, right? And then we have 3 conditions: R is less than L, R equals to L, and R is at least L. So this is the case that our old method still works on this theorem, and that's why we strictly bigger than L. So this is the case that our old method just modified works to prove this theorem, and which is why we have this condition. These two just wouldn't cooperate, these two cases, and that's where we're hoping to apply something new, try maybe induction. That's our next step, so that we can weaken some of these conditions. And of course, then there is this, okay, what happens to k-partite? And this bound that we get, this edge bound, is tight. The picture is probably exactly what you're thinking. So just have a, so let me, to show the tightness, you just take 3n minus L vertices and form a complete graph, take the L vertices and form complete tripartite, and then take this one vertex, connect it here, right? So that this picture gives the tightness, except it's not really too connected. So we feel that two connectedness could be dropped. It's just we weren't able to. Any questions?
Instead of dropping to a connectivity condition, what would happen if you raise it, say to 3 connected or 4 connected or something like that?
That's a great question. So one thing we have tried is saying, okay, we do want a 2 connectedness. How can we modify this edge, right? So if we do assume 2 connectedness and we're okay with it, then this edge condition could be improved, right? So that's one thing that we're working on right now. But Sandra, what you mentioned is also a good idea. We have not looked at that. And I can see it being useful because there's sigma k result that we could potentially use on the degree sum of vertices. So instead of looking at the Chen and Jacobson, you have only 2 vertices. There are sigma k results. Now you took some k vertices, right? But you need the k connectedness there. So definitely that could be another thing to try.
So let me make another comment about that. There are a lot of results about Hamiltonicity issues related to higher dimensional polyhedra. So there's a famous theorem that says that a n polytope has, for 3 polytopes, they have to be 3 connected and planar, the graphs, and that for higher dimensional polytopes, there's a theorem of the late Michel Belinsky that they have to be n connected. So there are a bunch of work by a variety of people, most notably by David Barnett, about conjectures and results about Hamilton circuits on 4 polytopes, and work by Gilkalai and others on higher dimensional polytopes.
Mm-hmm. Okay, thank you. We have not looked in that direction, but That could actually be very useful. Gabriella does discrete geometry, and I know she knows this a lot better than I do. So I'll suggest. Thank you.
So a small point, David Barnett's name is spelled B-A-R-N-E-T-T-E and Gilkalai is K-A-L-A-I.
Thank you.
Thank you. So let's see, are there any other questions for Zhanar or comments, suggestions?
Well, I have another comment for people who are interested in Hamilton. By the way, it was a very nice set of results and summary of these interesting history of this type of problem. So there's another very famous conjecture of David Barnett's about three-valent, three-connected bipartite graphs and whether they always have Hamilton circuits or not. And you leave out any of the conditions, and there are counterexamples known. But this very tight question of planar, three-valent, three-connected simple graphs, I think it's still open, but there's been a lot of progress on it recently. So I'm not familiar with all of the details. Maybe somebody has actually proved it by now.
Any other comments, questions? Otherwise, let's thank the speaker. Thank you, Zhanar.
Thank you so much. Thank you, everyone.